Everything you have ever experienced, every star that has ever burned, every thought that has ever crossed your mind, and every single event that has ever occurred in the entire history of the cosmos is governed by one single principle that most people completely misunderstand. And once you truly grasp what this principle means, you will never look at reality the same way again. There is a law in physics that dictates why time moves forward, why the universe is expanding, why you age, why ice melts in your drink, why civilizations rise and fall, and why life itself exists in the first place. This law is not gravity, it is not electromagnetism, and it is not the strong or weak nuclear force. It is something far more fundamental, something that operates behind the scenes of every single phenomenon in existence. From the smallest subatomic interaction to the largest cosmic event spanning billions of light years. This law is the second law of thermodynamics, and the concept at its heart is entropy. You are a slave to entropy. I am a slave to entropy. Every atom in the universe is a slave to entropy. And by the time you finish reading this, you will understand exactly why that statement is not hyperbole, but the literal truth about the nature of reality itself. Let us begin with something you do every single day without thinking about it. You open your refrigerator. Inside, food stays cold because the refrigerator is actively pumping heat from its interior and dumping that heat into your kitchen. The inside gets colder, sure, but your kitchen gets slightly warmer. The total entropy of the system, your kitchen plus the refrigerator, has increased. The heat has spread out more evenly across a larger space, and that spreading, that diffusion, that movement from concentrated to dispersed, is entropy in action. Now consider your smartphone. You charged it last night, storing electrical energy in a lithium-ion battery. Throughout the day, as you scroll through social media, send messages, and watch videos, that stored energy is converted into light from the screen, sound from the speakers, radio waves from the antenna, and most importantly, heat. That heat radiates away from your phone into the surrounding air, spreading out, becoming less concentrated, becoming less useful. The energy has not disappeared, it has merely transformed from a concentrated, useful form into a dispersed, useless form. That transformation is entropy increasing. Even the birth of a galaxy is not exempt from this principle. When a massive cloud of hydrogen gas collapses under its own gravity to form stars, it might seem like order is being created from chaos. After all, a star is a highly structured object with distinct layers, nuclear fusion occurring in its core, and a precise balance between gravitational collapse and radiation pressure. But look at what the star does once it forms. It radiates enormous quantities of light and heat into the surrounding space. Our own sun, for example, emits approximately 3.8 times 10 to the 26th power watts of energy every single second. That energy streams outward in all directions, filling the cosmos with photons that will never again be concentrated into a useful form. The entropy generated by the sun's radiation far exceeds the local decrease in entropy represented by the sun's organized structure. The universe, taken as a whole, has become more disordered because the sun exists, not less. And here is perhaps the most mind-bending example of all. Right now, as you process these words, as neurons fire in your brain and synapses transmit electrochemical signals, your brain is consuming energy. The human brain uses approximately 20 watts of power, roughly the same as a dim light bulb. And that energy is ultimately converted into heat that radiates from your skull into the surrounding environment. The very act of thinking, of forming memories, of understanding concepts increases the entropy of the universe. Your consciousness itself is an entropy-generating machine. From refrigerators to smartphones, from the formation of galaxies to the formation of thoughts in your mind, every single process that occurs anywhere in the universe drives entropy upward. This is not a suggestion or a guideline. It is an absolute, inviolable law of nature. So the question becomes, what exactly is entropy? Why does it always increase? And what does this mean for the fate of everything that exists? The word entropy was coined in 1865 by Rudolf Clausius, a German-born physicist who was working on understanding how heat engines operate. But the concept itself predates the word. It emerged from practical engineering problems during the Industrial Revolution. specifically from efforts to understand why steam engines could never convert all of their heat into useful work. There was always waste, always some energy that escaped as useless heat. And Clausius wanted to quantify this inevitable loss. He defined entropy as a thermodynamic quantity related to the amount of energy in a system that is unavailable to do work. In a closed system, one where no energy or matter enters or leaves, this quantity can never decrease. It can stay the same in idealized reversible processes, or it can increase in all real irreversible processes. This is the second law of thermodynamics, and it is one of the most fundamental principles in all of science. But this thermodynamic definition, while precise, does not really tell us what entropy is at a deeper level. For that, we need to turn to statistical mechanics and the work of Ludwig Boltzmann, one of the most brilliant and tragically underappreciated physicists in history. Boltzmann, working in the late 19th century, realized that the macroscopic properties we observe in the world, things like temperature, pressure, and entropy, are actually the result of the collective behavior of incomprehensibly large numbers of microscopic particles. A cup of coffee contains roughly 10 to the 25th power molecules, each moving in its own direction at its own speed, colliding with other molecules billions of times per second. We cannot possibly track each individual molecule, so instead we describe the system using macroscopic averages. Boltzmann's genius was to connect the microscopic world of individual particles to the macroscopic world of thermodynamics through a single, elegant equation that is now carved on his tombstone in Vienna. S equals K sub B times the natural logarithm of W. In this equation, S is the entropy, K sub B is the Boltzmann constant, which has a value of approximately 1.38 times 10 to the negative 23rd power joules per Kelvin. And W is the number of microstates consistent with the observed macrostate. This last part is the key to understanding everything. A microstate is a specific arrangement of all the individual particles in a system, their exact positions and velocities. A macrostate is the overall observable condition of the system, its temperature, pressure, volume, and so on. For any given macrostate, there are typically an astronomically large number of microstates that could produce that exact same macrostate. Entropy, according to Boltzmann, is simply a measure of how many microstates correspond to the macrostate you observe. Let me make this concrete with an example. Imagine you pour cream into a cup of black coffee. At first, there is a clear distinction between the dark coffee and the white cream. This separated state is a low-entropy macrostate because there are relatively few ways to arrange the coffee molecules and cream molecules such that they remain cleanly separated. There are specific constraints on where each type of molecule can be. Now wait a few minutes without stirring. The cream disperses throughout the coffee until the mixture is a uniform light brown color. This mixed state is a high-entropy macrostate because there are vastly more ways to arrange coffee, molecules and cream molecules in a mixed configuration than in a separated one. If you have 1,000 cream molecules and 1,000 coffee molecules in a container with 2,000 possible positions, the number of arrangements where all cream molecules happen to be on one side is vanishingly small compared to the number of arrangements where they are randomly distributed throughout. The mixed state has enormously more microstates than the separated state, which means it has enormously higher entropy. This is why cream mixes into coffee spontaneously, but never unmixes. It is not that unmixing violates any fundamental law of particle physics. Each individual molecular collision is perfectly reversible. If you could somehow reverse the velocity of every single molecule at a given instant, the system would retrace its steps and the cream would indeed separate back out from the coffee. But the probability of this happening spontaneously is so incredibly small that it might as well be 0. We are talking about probabilities like 1 divided by 10 to the power of 10 to the 25th. Numbers so small that they make the age of the universe seem like the blink of an eye. For all practical purposes, entropy always increases because there are overwhelmingly more high-entropy states than low-entropy states for any macroscopic system. Now, there are two common misconceptions about entropy that I need to address because they cause enormous confusion. The first misconception is that entropy increasing means energy is being destroyed or used up. This is completely wrong. Energy is always conserved. This is the first law of thermodynamics, and it is just as inviolable as the second law. When entropy increases, the total amount of energy in the universe does not change by even a single joule. What changes is the quality of that energy, its concentration, its usefulness. A fully charged battery and a dead battery contain the same total energy if you account for all the heat that was released during discharge. The difference is that the charged battery had its energy in a concentrated, low-entropy form that could be directed to do useful work, while the dead battery's energy has been dispersed as diffuse heat spread throughout the environment. Energy is never lost, it just becomes progressively less useful, less concentrated, more spread out. That is what entropy increase actually means in practical terms. The second misconception is more subtle. Many textbooks define entropy simply as disorder or randomness. And while this is not entirely wrong, it can be deeply misleading. The problem is that disorder is a subjective, qualitative term that does not have a precise scientific definition. What counts as disordered depends on your perspective. Is a crystal more ordered than a gas? Most people would say yes. But a crystal at absolute zero actually has zero entropy by the third law of thermodynamics, while the same atoms in a gaseous state have high entropy. So in this case, the common intuition about order and disorder aligns with the technical definition. But consider a different example. A living cell is incredibly complex and organized, far more so than a simple crystal. Does that mean a cell has lower entropy than a crystal? Not necessarily, because entropy depends on the number of accessible microstates, not on how complex or beautiful or organized something appears to our human perception. The correct definition of entropy is always Boltzmann's. It is proportional to the logarithm of the number of microstates consistent with the macroscopic constraints. Disorder is at best a rough analogy, and at worst a source of serious confusion. Having established what entropy actually is, let us now confront one of the deepest mysteries in all of physics. Why does time have a direction? Think about it carefully. The fundamental equations of physics, whether we are talking about Newton's laws of motion, Maxwell's equations of electromagnetism, the Schrödinger equation of quantum mechanics, or even Einstein's equations of general relativity, are all time-symmetric. This means that if you take any solution to these equations and replace every instance of the time variable t with negative t, you get another perfectly valid solution. The laws of physics work just as well running backward as they do running forward. If you watched a movie of two billiard balls colliding and someone played it in reverse, you would not be able to tell which version was the real one, because both versions are consistent with Newton's laws. Yet our everyday experience is filled with processes that clearly have a preferred direction in time. A coffee cup falls off a table and shatters on the floor, but we never see broken fragments leap off the floor and reassemble into an intact cup. An ice cube melts in a glass of warm water, but we never see a glass of lukewarm water spontaneously form an ice cube while the remaining water becomes warmer. A person ages and eventually dies, but we never see a corpse spontaneously reassemble into a living person. We call this the arrow of time, and it is one of the most profound asymmetries in all of nature. We can remember the past, but not the future. We can influence the future, but not the past. Causes always precede their effects, never the other way around. But if the fundamental laws of physics are time-symmetric, where does this arrow come from? The answer, as you have probably guessed, is entropy. The second law of thermodynamics is the only fundamental law of physics that is not time-symmetric. It singles out a preferred direction in time, the direction in which entropy increases. The past is the direction of lower entropy, and the future is the direction of higher entropy. When you see a cup shatter, you are watching entropy increase as a low-entropy state of a single intact cup transforms into a high-entropy state of many scattered fragments and dissipated heat. The reverse process would require entropy to decrease, which is so extraordinarily improbable that it effectively never happens for macroscopic systems. This is the arrow of time. It is not built into the fundamental dynamical laws of physics. It is a consequence of the statistical behavior of vast numbers of particles, combined with a very special boundary condition at the beginning of the universe. And this brings us to perhaps the deepest question of all about entropy and time. If the laws of physics are time-symmetric, and if entropy increase is just a matter of statistics and probability, then the second law of thermodynamics has an uncomfortable implication. It tells us that if we look toward the future, entropy will be higher. But by the exact same statistical reasoning, if we look toward the past, entropy should also be higher. After all, the same argument that says a system will most likely evolve toward higher entropy in the future also says it most likely evolved from higher entropy in the past. Yet this contradicts our observation that the past had lower entropy than the present. The resolution of this paradox is that the second law of thermodynamics is not really a law in the same sense as Newton's laws or Maxwell's equations. It is a statistical tendency that only works in one temporal direction because of a very specific initial condition. The universe began in an extraordinarily low entropy state roughly 13.8 billion years ago at the Big Bang. This is sometimes called the past hypothesis, a term coined by philosopher David Albert, though the idea goes back to Boltzmann himself and was developed extensively by Roger Penrose. Consider what the universe looked like shortly after the Big Bang. It was incredibly hot, dense, and remarkably uniform. The cosmic microwave background radiation, which is a snapshot of the universe when it was only about 380,000 years old, shows that matter and energy were distributed with a uniformity of better than 1 part in 100,000. This might seem like a high-entropy state because it appears smooth and featureless. But appearances are deceiving. When you include gravity in the picture, a perfectly smooth distribution of matter is actually an extremely low-entropy state. Why? Because gravity is an attractive force that tends to clump matter together. The highest entropy state for a gravitating system is not a smooth, uniform distribution. It is a state where matter has clumped into the most concentrated possible configuration. A black hole. In fact, Roger Penrose calculated that if the matter in the observable universe were in its highest entropy gravitational configuration, it would form a single enormous black hole with an entropy of approximately 10 to the 123rd power. Compare this to the actual entropy of the observable universe today, which is estimated at roughly 10 to the 104th power, still overwhelmingly dominated by supermassive black holes. The entropy of the early universe was far lower still. This means the Big Bang represented an incredibly special, improbable initial condition. A universe that was about as far from gravitational equilibrium as it could possibly be. This is the ultimate source of the arrow of time. The universe started in a spectacularly unlikely low-entropy state, and everything that has happened since, every star that has formed, every planet that has coalesced, every living thing that has evolved, every thought that has been thought, is part of the long, inexorable slide toward higher entropy. The past has lower entropy than the present because the Big Bang had low entropy. The future will have higher entropy than the present because that is where statistics leads when you start from a low entropy initial condition. We remember the past but not the future because memory formation is an entropy increasing process that can only proceed in the direction of increasing entropy. We feel that causes precede effects because causal processes are entropy increasing processes. The entire fabric of our temporal experience is woven from the thread of entropy increase, which in turn traces back to the extraordinary initial conditions of the universe. But why did the universe start in such a low entropy state? This is one of the great unsolved problems of physics and cosmology. Penrose himself has emphasized how special the initial conditions must have been. He estimates that the probability of the universe starting in such a low-entropy state by random chance is approximately 1 in 10 to the power of 10 to the 123rd, a number so inconceivably small that there is nothing in human experience to compare it to. Some physicists appeal to inflationary cosmology, suggesting that a brief period of exponential expansion in the early universe might explain the smoothness and uniformity of the initial state. Others suggest that our universe might be one of an enormous number of universes in a multiverse, and that the low-entropy initial conditions are simply a selection effect. We can only exist in a universe that started with low enough entropy to permit the formation of complex structures like ourselves. Still others, like Penrose with his conformal cyclic cosmology, suggest that the Big Bang was not really a beginning, but rather a transition from a previous aeon of the universe, where the endpoint of one expanding universe smoothly connects to the beginning of the next through a conformal rescaling of the geometry. None of these proposals is universally accepted, and the mystery of the past hypothesis remains one of the deepest open questions in physics. Let us now turn our attention to the future and ask what entropy has to say about the ultimate fate of the universe. If entropy always increases and the universe is a closed system, then eventually, perhaps in the incomprehensibly distant future, the universe must reach a state of maximum entropy. This state is known as heat death, and it represents the ultimate thermodynamic equilibrium of the cosmos. The concept was first articulated in the 19th century by Lord Kelvin and Hermann von Helmholtz, who realized that the second law of thermodynamics implied a bleak future for the universe. Eventually, all energy differences would be smoothed out, all temperature gradients would equilibrate, and no further work of any kind could be performed. The universe would become a vast, cold, featureless expanse of uniform temperature, with nothing ever happening again for all eternity. Modern cosmology has refined this picture considerably, and the details are both fascinating and sobering. Let me walk you through the timeline of the universe's future as best we understand it. For the next several trillion years, stars will continue to form in galaxies, burning hydrogen and helium into heavier elements. But the supply of hydrogen gas available for star formation is finite, and galaxies are gradually using it up. Within about 100 trillion years, give or take, the last stars will have burned out. The universe will be populated by the remnants of dead stars, white dwarfs slowly cooling toward absolute zero, neutron stars spinning down and dimming, and black holes of various sizes lurking in the darkness. This era, sometimes called the degenerate era, will last an unfathomably long time. White dwarfs will gradually cool over something like 10 to the 15th power years until they become cold. Dark objects sometimes called black dwarfs. If protons decay, as some theories of particle physics suggest, then even these remnants will eventually disintegrate over timescales of perhaps 10 to the 40 power years, leaving behind only a thin gruel of electrons, positrons, photons, and neutrinos. But the most dramatic story in the far future concerns black holes. Black holes are the highest entropy objects in the universe, as I mentioned earlier. A black hole with the mass of our Sun would have an entropy of approximately 10 to the 77th power in natural units, which is roughly 10 to the 19 times higher than the entropy of the Sun itself as a normal star. Supermassive black holes at the centers of galaxies, which can have masses of billions of solar masses, have correspondingly higher entropies still. In fact, the entropy budget of the observable universe today is completely dominated by supermassive black holes, which together account for roughly 10 to the 104th power units of entropy, dwarfing the contribution from all other sources combined. But even black holes are not eternal. In 1974, Stephen Hawking made one of the most remarkable theoretical discoveries in the history of physics. Black holes radiate. Due to quantum mechanical effects near the event horizon, black holes emit a faint thermal radiation now called Hawking radiation, and this radiation causes them to slowly lose mass and shrink over time. The temperature of this radiation is inversely proportional to the mass of the black hole, so large black holes radiate incredibly slowly. A black hole with the mass of the Sun would have a temperature of only about 60 billionths of a Kelvin, far colder than the current cosmic microwave background temperature of 2.7 Kelvin. This means that today, stellar mass and supermassive black holes are actually gaining more energy from the cosmic microwave background than they lose through Hawking radiation, so they're growing rather than shrinking. But as the universe continues to expand and cool, the cosmic microwave background temperature will eventually drop below the Hawking temperature of even the largest black holes, at which point they will begin to evaporate in earnest. The evaporation time for a black hole is proportional to the cube of its mass. For a solar mass black hole, the evaporation time is approximately 10 to the 67th power years. For a supermassive black hole of 10 billion solar masses, it would be around 10 to the 100th power years. These are numbers so large that they defy any attempt at intuitive comprehension. But they are finite, Eventually, every black hole in the universe will evaporate, releasing its stored entropy back into the cosmos as a bath of incredibly low-energy Hawking radiation. After the last black hole evaporates, the universe enters what physicists call the dark era. By this point, the universe has expanded to such an enormous size that any remaining particles are separated by distances far greater than the current observable universe. The temperature has dropped to a fraction of a degree above absolute zero, perhaps 10 to the negative 30th power Kelvin or lower. Nothing happens. Nothing can happen. There are no energy gradients to drive any processes. No temperature differences to allow any heat engine to operate. No concentrations of matter to allow any gravitational collapse. The universe has reached thermodynamic equilibrium, maximum entropy. This is heat death. It is not death by heat in the colloquial sense. It is death of all thermal gradients. Death of all differences, death of all change. It is the ultimate democratic state of the universe, where every part of space is identical to every other part, and the arrow of time itself becomes meaningless because there is no longer any direction in which entropy can increase. Is this truly the end? Perhaps, but perhaps not. Penrose's conformal cyclic cosmology suggests that in the infinite future, when all massive particles have either decayed or been diluted away by the expansion, the universe becomes conformally flat and indistinguishable, mathematically speaking, from the Big Bang singularity of a new universe. In this picture, the heat death is not an ending but a transition, and the universe cycles eternally through successive eons, each beginning with a Big Bang and ending with a heat death that seamlessly becomes the next Big Bang. This is a speculative and controversial idea, but it offers a strange kind of hope, that even the ultimate victory of entropy might somehow contain the seeds of its own renewal. Now let us address what might seem like a paradox. If entropy always increases and the universe tends toward disorder, how is it possible that complex, organized structures like galaxies, stars, planets, and living organisms exist? After all, a living human body is an extraordinarily ordered arrangement of approximately 37 trillion cells, each containing billions of precisely arranged molecules, all working together in an intricate dance of biochemistry that maintains life against the relentless tide of entropy. How can such order exist in a universe governed by the second law? The resolution of this apparent paradox is one of the most important insights in all of physics. The second law applies to closed systems, but living organisms are not closed systems. They are open systems that exchange energy and matter with their surroundings. A living organism maintains its internal order not by violating the second law, but by exporting entropy to its environment. Every living thing takes in low-entropy energy from its surroundings, uses that energy to maintain and build its internal structure, and then releases high-entropy waste energy, primarily in the form of heat, back into the environment. The decrease in entropy within the organism is more than compensated by the increase in entropy outside it. So the total entropy of the system plus its environment always increases, exactly as the second law demands. This insight was beautifully articulated by Erwin Schrödinger in his famous 1944 book, What Is Life? Schrödinger wrote that a living organism feeds on negative entropy, or negentropy as he called it, extracting order from its environment to maintain its own organized state. For animals like us, the source of this negentropy is food, complex organic molecules that contain chemical energy in highly organized molecular bonds. We break these bonds through metabolism, using the released energy to power our cellular machinery. And we excrete the leftover atoms in highly disordered forms like carbon dioxide, water vapor, and heat. A human body at rest produces approximately 80 to 100 watts of heat. And this heat represents entropy being dumped into the environment to pay the thermodynamic cost of staying alive. For the biosphere as a whole, the ultimate source of low-entropy energy is the sun. Plants capture photons from the sun, which arrive as relatively low-entropy radiation with a color temperature of about 800 Kelvin, and use that energy to build complex organic molecules from simple ingredients like carbon dioxide and water. The plants then re-radiate the same amount of energy back into space, but at the much lower temperature of Earth's surface, roughly 255 Kelvin, when averaged appropriately for radiation balance. Because the same amount of energy is radiated at a much lower temperature, it is carried by many more photons, each of lower energy, which means it has much higher entropy. The net effect is that Earth absorbs low-entropy solar radiation and emits high-entropy infrared radiation. And the difference in entropy between these two streams is what powers all of life on Earth. The biosphere is essentially an entropy pump, using the flow of solar energy to maintain a local pocket of low entropy on Earth's surface while increasing the total entropy of the solar system. This leads to a profound and somewhat unsettling perspective on the role of life in the universe. If we step back and look at life from a purely thermodynamic perspective, living organisms are not fighting against entropy. They are servants of entropy. They are machines that accelerate the production of entropy by converting concentrated, high-quality energy into dispersed, low-quality heat far more efficiently than simple non-living processes could. A barren rock illuminated by sunlight will absorb the radiation and re-emit it as infrared, increasing entropy in the process. But a forest covering that same rock will intercept the sunlight, use it to drive an enormously complex web of biochemical reactions, and in the process generate entropy far faster and more efficiently than the bare rock alone. Life is an entropy accelerator. This idea has been formalized and extended by Jeremy England, a physicist at the Massachusetts Institute of Technology, who in 2013 published a theoretical paper proposing what he calls dissipation-driven adaptation. England's theory suggests that under certain conditions, matter will spontaneously self-organize into structures that are particularly effective at dissipating energy and producing entropy. Given a source of energy and a heat bath to absorb waste heat, random collections of molecules will tend to evolve over time toward configurations that absorb and dissipate energy more and more efficiently. England argued that this thermodynamic tendency might help explain the origin of life itself. The emergence of self-replicating molecules and eventually living cells could be understood not as a miraculous accident, but as a natural consequence of the second law of thermodynamics driving matter towards states of maximal entropy production. This is a bold and still controversial claim, and it certainly does not replace the detailed biochemical understanding of how life actually arose on Earth. The origin of life remains one of the great unsolved problems in science. But England's framework offers an intriguing thermodynamic perspective. Perhaps life is not something that happened despite the second law of thermodynamics, but because of it. Perhaps the universe generates life as a means of increasing its entropy more efficiently, just as it generates stars and galaxies and weather systems and ocean currents, all of which are dissipative structures that accelerate the flow from low entropy to high entropy. In this view, you and I and every other living thing are not rebels against the cosmic order. We are its most sophisticated tools. Consider how this plays out at the molecular level. When DNA replicates, it creates a highly ordered copy of genetic information. This seems like a decrease in entropy, and locally it is. But the energy required to drive DNA replication comes from the hydrolysis of nucleotide triphosphates, which releases heat into the surrounding water. The entropy increase of the environment due to this released heat far exceeds the entropy decrease represented by the new, ordered DNA molecule. Similarly, when a cell divides, creating two organized daughter cells from one mother cell, the metabolic processes that power cell division release heat and produce waste products that increase the entropy of the surroundings by far more than the entropy decrease of creating a new organized cell. Every act of biological organization is paid for with a far larger act of environmental disorganization. The human brain provides perhaps the most dramatic example of this principle. The brain is arguably the most complex organized structure in the known universe, containing approximately 86 billion neurons connected by roughly 100 trillion synapses, with each neuron firing between 1 and 100 times per second. Maintaining this extraordinary level of organization requires enormous energy input. The brain consumes about 20% of the body's total energy budget despite accounting for only about 2% of its mass. This energy is used to maintain ion gradients across neural membranes, synthesize neurotransmitters, transport molecules along axons, and perform the countless other metabolic tasks required for neural function. All of this energy is ultimately converted to heat that radiates away from the skull, increasing the entropy of the environment. Every thought you think, every memory you form, every decision you make has a thermodynamic cost measured in entropy generated. There is actually a precise lower bound on the thermodynamic cost of information processing, and it connects beautifully to the relationship between entropy and information that we need to discuss next. In 1961, Rolf Landauer at IBM proved that erasing one bit of information requires dissipating at least K sub B times T times the natural logarithm of 2 joules of energy as heat, where T is the temperature of the environment. At room temperature of about 300 Kelvin, this works out to approximately 2.87 times 10 to the negative 21st joules per bit erased. This is called the Landauer limit or Landauer's principle, and it represents a fundamental connection between information and thermodynamics. Information is physical, as Landauer famously stated, and manipulating information has inescapable thermodynamic consequences. This brings us to one of the most profound intellectual connections of the 20th century, the deep relationship between thermodynamic entropy and information. In 1948, Claude Shannon at Bell Labs was working on the mathematical theory of communication and needed a way to quantify the amount of information in a message. He defined a quantity that measures the uncertainty or unpredictability of a random variable. And when he showed his formula to the mathematician John von Neumann reportedly told him to call it entropy because the formula was identical to Boltzmann's entropy formula and because nobody really understands entropy. So in a debate, you will always have the advantage. Whether this anecdote is precisely true or not, Shannon did call his quantity entropy. And the mathematical parallel between Shannon's information entropy and Boltzmann's thermodynamic entropy turned out to be far more than a superficial resemblance. It reflects a deep unity between the concepts of information, probability, and physics. Shannon's entropy for a discrete random variable x that can take values x1, x2, through xn with probabilities p1, p2, through Pn is defined as h of x equals negative the sum of p sub I times log base 2 of p sub I, with units of bits. This measures the average amount of information gained, or equivalently the average amount of uncertainty resolved, when you learn the value of x. If x is a fair coin flip, h equals 1 bit. If x is the roll of a fair 6-sided die, h equals log base 2 of 6, which is about 2.585 bits. If x is certain, meaning one outcome has probability 1, then h equals 0 bits because there is no uncertainty to resolve. The Shannon entropy is maximized when all outcomes are equally likely, which corresponds to maximum uncertainty, maximum surprise, maximum information content. Now compare this with Boltzmann's thermodynamic entropy. If a system has W equally likely microstates, then the thermodynamic entropy is S equals K sub B times ln W, converting to bits using the relation ln W equals log base 2 of W times ln 2. We get S equals K sub B times ln 2 times log base 2 of W. The log base 2 of W is exactly the Shannon entropy if we consider the microstate of the system as a random variable with W equally likely outcomes. The thermodynamic entropy is literally proportional to the information entropy, with the Boltzmann constant times ln2 as the conversion factor. This means that thermodynamic entropy can be interpreted as a measure of missing information. It tells you how many bits of information you would need to specify the exact microstate of the system, given that you only know its macrostate. This informational interpretation of entropy resolves many apparent puzzles and provides deep insight into the nature of the second law. When entropy increases, it means that information about the detailed microstate of the system is being lost. Consider the coffee and cream example again. Initially, when the cream and coffee are separated, you have some information about the system. You know roughly where the cream molecules are and where the coffee molecules are. As they mix, this information is lost. After complete mixing, you have no idea which molecules used to be in the cream and which used to be in the coffee. Information has been dispersed, scrambled, made practically unrecoverable. This is entropy increase viewed through the lens of information theory. This informational perspective also resolves the famous puzzle of Maxwell's demon, one of the most celebrated thought experiments in the history of physics. In 1867, James Clerk Maxwell imagined a tiny intelligent being stationed at a small door between two chambers of gas at the same temperature. The demon observes individual molecules and selectively opens the door to allow fast-moving molecules to pass into one chamber and slow-moving molecules into the other. Over time, one chamber becomes hot and the other becomes cold, apparently decreasing the entropy of the system without any work being done. This seems to violate the second law of thermodynamics. The resolution, which took over a century of debate to fully clarify, involves the demon's memory. To operate the door effectively, the demon must observe, record, and process information about each molecule. This information must be stored somewhere in the demon's memory. Eventually, the demon's memory fills up and must be erased to continue operation. By Landauer's principle, erasing each bit of memory dissipates at least K sub B times T times ln 2 joules of energy as heat, which increases the entropy of the environment. When you carefully account for the entropy generated by the demon's information processing, it turns out that the total entropy of the system, gas plus demon plus environment, always increases, exactly as the second law demands. The demon cannot violate the second law because the second law already accounts for the thermodynamics of information processing. Information, it turns out, is not free. It has a physical substrate, a thermodynamic cost, and an inextricable connection to entropy. In recent years, experimental physicists have actually built real-world versions of Maxwell's demon using nanoscale electronic circuits and feedback control systems. In 2010, Shoichi Toabe and colleagues at Tsui University in Tokyo demonstrated a molecular-scale device that could use information feedback to convert thermal energy into directed motion, effectively extracting work from a single heat bath at the apparent expense of the second law. However, careful analysis confirmed that when the entropy cost of the measurement and feedback electronics was included, the total entropy still increased. These experiments beautifully confirm the intimate connection between information and thermodynamics, and demonstrate that Landauer's principle is not merely theoretical, but has direct physical consequences at the nanoscale. The information-theoretic view of entropy also has profound implications for our understanding of black holes and quantum gravity. In 1972, Jacob Bekenstein proposed that black holes have entropy proportional to the area of their event horizon, measured in units of the Planck area, which is approximately 2.6 times 10 to the negative 70 square meters. Specifically, the Bekenstein-Hawking entropy of a black hole is S equals K sub B times A divided by 4 times the Planck length squared, where A is the area of the event horizon. For a black hole with the mass of the Sun, this gives an entropy of approximately 10 to the 77th power in natural units, or equivalently, the black hole can store about 10 to the 77th power bits of information. This is an almost incomprehensibly large number, far exceeding the entropy or information content of any other object of comparable size. The fact that black hole entropy is proportional to area rather than volume is deeply puzzling and has led to one of the most important ideas in theoretical physics, the holographic principle, first proposed by Gerard T. Hooft and later developed by Leonard Susskind. The holographic principle suggests that the maximum amount of information that can be contained in any region of space is proportional to the surface area of that region, not its volume. This implies that the three-dimensional world we experience might in some sense be a projection of information encoded on a two-dimensional surface, much like a hologram. While this sounds bizarre, it has received strong theoretical support from Juan Meldesena's 1997 ADS/CFT correspondence, which provides a concrete mathematical realization of the holographic principle in certain theoretical contexts. If the holographic principle is correct, it means that the fundamental nature of reality is informational, and that entropy, the measure of information or its absence, is truly the most fundamental quantity in physics. The connection between black holes and information leads to another famous puzzle, the black hole information paradox. When matter falls into a black hole, all information about its detailed quantum state appears to be lost behind the event horizon. If the black hole then evaporates via Hawking radiation, as quantum mechanics predicts, the radiation appears to be purely thermal, carrying no information about what fell in. This would mean that information has been irreversibly destroyed, which violates a fundamental principle of quantum mechanics called unitarity, the principle that quantum evolution is always reversible. This paradox has generated enormous theoretical activity over the past 50 years, with proposed resolutions ranging from black hole complementarity to the firewall hypothesis to recent ideas about quantum entanglement between the interior and exterior of the black hole. The resolution of the information paradox, when it is finally achieved, will likely reveal something profound about the relationship between quantum mechanics, gravity, information, and entropy. Many physicists believe that understanding how information is preserved in black hole evaporation is the key to achieving a quantum theory of gravity, the long-sought unification of general relativity and quantum mechanics. Let us now step back and consider the big picture of what entropy tells us about the nature of reality. We have seen that entropy is connected to time, determining its direction and making the past fundamentally different from the future. We have seen that entropy governs the fate of the universe, driving it inexorably toward heat death. We have seen that entropy is intimately related to life, which exists not in defiance of the second law, but as its most efficient servant. And we have seen that entropy is fundamentally about information, measuring what we do not know about the detailed state of a system. All of these threads weave together into a picture of reality that is both humbling and awe-inspiring. Here is one way to think about it. The universe began approximately 13.8 billion years ago in a state of extraordinarily low entropy, a state of immense potential, like a tightly wound cosmic spring. Everything that has happened since, every star that has ignited, every planet that has formed, every living thing that has evolved, every civilization that has risen, is powered by the unwinding of that spring, by the flow from low entropy to high entropy. We live in the gradient. We exist because entropy has not yet reached its maximum, because there are still energy differences to exploit, still temperature gradients to drive processes, still order to be found and used and ultimately dissipated. When we eat food, we are exploiting the entropy gradient between concentrated chemical energy and dispersed heat. When we think thoughts, we are exploiting the entropy gradient between organized neural activity and the background thermal noise of the brain. When we build civilizations, we are exploiting the entropy gradient between concentrated solar energy and the cold void of outer space. In a very real sense, all of human civilization is an entropy machine. We take low-entropy fossil fuels, concentrated solar energy stored by ancient organisms over millions of years, and burn them to power our industries, our transportation, our agriculture, and our technology. In the process, we convert that concentrated energy into dispersed heat, carbon dioxide, and other waste products, increasing the entropy of Earth's surface environment. The entire global economy, with its output of approximately $100 trillion per year, is fundamentally a process of converting low-entropy resources into high-entropy waste while extracting useful work in between. Our energy consumption of roughly 580 exajoules per year represents entropy production on a planetary scale. Climate change, pollution, resource depletion, these are all manifestations of entropy increase, of useful concentrated resources being dispersed into useless diffuse waste. But there is another side to this story, one that offers a more hopeful perspective. Yes, we are entropy producers. Yes, the universe is slowly dying as entropy inexorably increases. But in the interim, in the vast span of time between the Big Bang and heat death, the flow of entropy from low to high powers the creation of extraordinary complexity. Stars are complex. Galaxies are complex. Planetary systems are complex. Life is complex. Consciousness is complex. Culture, art, science, love. These are all complex phenomena that exist only because entropy has not yet reached its maximum, because the universe is still in the process of unwinding from its extraordinarily special initial conditions. We are transient patterns of local order, sustained by the flow of entropy from concentrated to dispersed, from past to future, from improbable to probable. We are eddies in the entropic stream, momentary swirls of complexity generated by the rushing current of the second law. There is a beautiful analogy here with a river. A river flows downhill, driven by gravity. This flow is irreversible in the same way that entropy increase is irreversible. Water does not spontaneously flow uphill. But as it flows downhill, the river creates extraordinary complexity along its path, eddies. Whirlpools, rapids, waterfalls, oxbow lakes, deltas, ecosystems teeming with life. None of these complex structures violate the downhill flow of the river. They are created by it. They exist because of the gradient. Because the water has somewhere higher to start from and somewhere lower to end up. In the same way, the flow from low entropy to high entropy creates all the complexity and structure and life we see in the universe. We are the eddies in the cosmic river of entropy. And our existence is not despite the second law but because of it. This perspective also offers a kind of existential reassurance. It is easy to feel nihilistic when confronted with the heat death of the universe. If everything is going to end in cold, featureless equilibrium anyway, what is the point of anything? But consider this. The heat death is projected to occur on timescales of 10 to the 100th power years or longer. The current age of the universe is only about 1.38 times 10 to the 10th power years. We are still in the very earliest stages of the universe's history, still in the first flush of youth after the Big Bang. The universe has barely begun to unwind. There is an almost incomprehensible amount of time remaining before heat death. And during that time, the entropic gradient will continue to power the creation of complexity. Perhaps complexity far beyond anything we can currently imagine. Moreover, the thermodynamic arrow of time is precisely what makes experience and meaning possible. Without the entropy gradient, without the arrow of time, there would be no before and after. No cause and effect, no memory, no anticipation, no narrative, no life. The very fact that entropy increases is what makes it possible for things to happen, for stories to unfold, for beings to exist who can contemplate their own existence. Entropy is not the enemy of meaning. It is the precondition for meaning. A universe in thermal equilibrium would be a universe without meaning, without experience, without anything. It is only because the universe is out of equilibrium, only because entropy has not yet reached its maximum, that anything matters at all. Let me close with one final observation that ties together everything we have discussed. Entropy, information, and existence are three aspects of the same underlying reality. Entropy measures the number of possible microscopic configurations of a system. Information is what distinguishes one configuration from another. Existence. The fact that this particular universe with these particular laws and this particular history is real rather than some other possibility is itself a matter of information, of one actuality being selected from among countless possibilities. The fact that we exist, that we are here, that we can ask why we are here, is intimately connected to the entropic history of the universe. We exist because the universe started in a special low-entropy state, because entropy increase powered the creation of stars and planets and chemistry and biology and evolution and consciousness, and because the arrow of time created by entropy increase makes it possible for information to accumulate, for memories to form, for knowledge to grow, for civilizations to develop. We are entropy's children. We are born from the gradient between the hot dense beginning and the cold empty end. We live in the flow, sustained by the current, creating our small pools of local order while contributing to the grand dissipation of the cosmos. We are how the universe contemplates its own nature, how entropy becomes aware of itself, how information processes itself. And perhaps that is enough. Perhaps the fact that the universe has generated beings capable of understanding entropy, of grasping the second law of thermodynamics, of comprehending their own place in the cosmic unfolding, is itself the most remarkable thing that the entropic gradient has ever produced. We are the universe's way of understanding itself. And we exist because entropy makes understanding possible. The next time you stir cream into your morning coffee and watch it swirl into a uniform tan, remember that you are watching the same process that created you, that created the earth, that created the stars, that drives the expansion of the cosmos, and that will ultimately lead to the heat death of the universe billions upon billions of years from now. You are watching entropy increase. You are watching time flow. You are watching the universe do what it has always done and will always do, spread out, mix together, smooth over, dissolve distinctions, and in the process, create fleeting marvels of complexity and beauty along the way. You are one of those marvels. And for a brief, shining moment in the vast history of the cosmos, you are here, aware, alive, and capable of appreciating the extraordinary improbability of your own existence in a universe ruled by the most democratic, the most inevitable, and the most creative law of all, the law of entropy.